cosmic structures larger than our theories allow, galaxies appearing mature billions of years ahead of schedule, an expansion rate that refuses to line up with our equations. Webb's 2025 discoveries sharpen a set of genuine puzzles, some confirmed, others still debated, that strike at the foundation of how we think the cosmos began. In this video, we'll survey what Webb found, why standard models struggle, what alternate physics or cyclic ideas propose, and where the evidence is strongest or weakest. And among the most striking puzzles lies a mystery in the earliest galaxies, massive systems that should not exist. Galaxies that shouldn't exist. When astronomers began studying the faint light from galaxies that appeared only 300 to 700 million years after the Big Bang, expectations were modest. Models suggested they should be small and irregular, clumps of stars forming without symmetry or order, since gravity and time had not yet shaped them. What Webb actually found was starkly different. Its infrared eye revealed multiple candidate galaxies, whose inferred stellar masses and organized structures appeared much larger and far more mature than theory had predicted for that early epoch. Several looked disproportionately developed, vast collections of stars arranged into coherent systems when space itself was still thought to be chaotic. These surprising candidates earned the label universe breakers because they broke assumptions about how galaxies should first emerge. The more Webb observed, the deeper the tension grew. Standard formation models anticipate a slow buildup, with matter needing billions of years to coalesce into massive galaxies like spirals or giant ellipticals. Instead, Webb captured systems where stars were already arranged in disks or central bulges far sooner than expected. Their luminosity implied large stellar populations, and in several cases heavy elements were present, meaning that earlier generations of stars had already formed, lived, and died in rapid succession. Interpreted literally, this was growth happening orders of magnitude faster than permitted by consensus models. Some of Webb's clearest cases sharpened the point. In fields like CERS and Cosmos Webb, candidate galaxies stood out not as faint smudges, but as robust structures containing enough light to imply stellar masses well above what simulations predicted for such an early age. Their apparent sizes rivaled galaxies billions of years older. Measurements of orbiting gas clouds suggested deep gravitational wells, an unmistakable indicator of large-scale maturity. These snapshots of the young universe showed not scattered fragments, but coherent and active systems. At the same time, astronomers caution against treating early numbers as definitive. Redshift estimates for some universe-breaker candidates initially came from photometric data, essentially color measurements, rather than detailed spectra. Later spectroscopic analysis showed that a few of the most jaw-dropping examples were closer or less massive than first thought. This does not eliminate the puzzle, but it underscores the need for care. Some follow-up work shows measurement and selection affects matter, so researchers are investigating both astrophysical and observational explanations. The picture is not total upheaval, but it is a consistent indication that something fundamental is being missed. What makes these discoveries particularly difficult is how consistent the evidence has become. One or two unusual galaxies could be dismissed as chance alignments or misinterpretations. But Webb has found not just isolated examples, but a population of mature candidates distributed across survey fields. That consistency hints at a broader pattern in cosmic dawn, not merely a statistical fluke. It is this weight of recurrent evidence, not a single outlier, that convinces astronomers the issue is real. The contradiction leaves researchers at a fork in the road. Either galaxy formation proceeded differently in the first few 100 million years, requiring major revisions to current models, or the early universe retained imprints from some deeper history. The first path demands changes to our understanding of star formation, cooling, and feedback. Perhaps conditions let stars ignite almost immediately as gas collected, or dark matter structures accelerated the timeline by drawing gas in more efficiently than predicted. The second path leaves space for more radical, speculative interpretations, such as cyclical universes where remnants carry across expansions. Researchers emphasize that such scenarios remain highly conjectural, but the fact they are even considered shows how far Webb has pushed cosmology from its comfort zone. Regardless of interpretive stance, the central fact is difficult to ignore. The early universe seems structured faster and more richly than textbooks described. Instead of a gradual accumulation of complexity, Webb presents an image of sudden richness, a bloom of galaxies when the universe was less than 1 billion years old. Theories tuned to slower, incremental growth cannot yet reproduce what the telescope records. For cosmologists, these findings are more than anomalies. They challenge the scaffolding on which much of modern astrophysics is built. Simulations run on supercomputers, coded to obey established rules of cooling, feedback, and clustering, fail to produce galaxies comparable to what Webb sees at high redshift. Adjustments can narrow the gap, but no small tweak fully closes it. This leaves researchers weighing whether the missing pieces belong to new physics, more accurate observations, or deeper cosmological revisions. Some responses have focused on dark matter. If its properties differ slightly from the collisionless behavior assumed in models, then structures might assemble faster than expected, seeding galaxies earlier. Others look to high efficiencies in early star formation, suggesting once gas gathered, it converted into stars rapidly. Still others argue feedback, the cycle of stellar winds and supernovae, might have acted differently under primordial conditions. Each line of thought tries to make the accelerated growth less mysterious while staying within known physics. Yet none provides a single convincing resolution on its own. The radical possibilities, though firmly speculative, remain in circulation as well. Cyclic universes, pre-Big Bang remnants, or physics beyond the standard model sometimes enter the conversation. The important qualification is that these scenarios are not presented as default explanations, but as imaginative boundaries, reminding us of the scale of the mystery. For most astronomers, the priority remains refining observations, calibrations, and models before reaching for ideas beyond established physics. Meanwhile, Webb's catalogs continue to grow. Each new survey deepens the impression of an early cosmos more complex than anticipated. Population counts suggest an abundance of galaxies where only sparse, small ones were thought possible. The light from these systems, already enriched with elements heavier than hydrogen and helium, confirms a fast cycle of stellar birth and death compressed into a narrow span of time. None of this dissolves earlier successes of the Big Bang framework, but it demands modification where predictions falter. Even within healthy scientific caution, the result is inescapable. Our models did not anticipate galaxies of this size and maturity so early. Whether due to missing physics or deeper cosmological structure, the observations force a reevaluation. Webb has closed off the option of pretending that the young universe was empty, slow, and primitive. Instead, it gives us a cosmos that appears busy and advanced at an age when simplicity was supposed to rule. And this is only one side of the telescope's 2025 surprises. Alongside galaxies that raise questions about time and growth, Webb has also sharpened a second, equally fundamental problem: the rate of cosmic expansion. That issue, far from converging, has only grown more pronounced in the wake of these latest observations. The Hubble constant problem deepens. For cosmologists, one of the most enduring puzzles is also one of the most basic. How quickly is space itself stretching? This is the essence of the Hubble constant, a single number meant to describe the present-day speed at which galaxies drift apart. In principle, it should be straightforward: measure the expansion, compare methods, and find agreement. In practice, however, different approaches yield stubbornly incompatible results, and instead of shrinking, the divide has only become sharper in recent years. This ongoing mismatch is now called the Hubble Tension. Two main camps define the conflict. One is based on observations of the local universe. Supernovae, variable stars, and other standard candles give expansion rates around 73 kilometers per second per megaparsec. This work, led by the SH0Es collaboration headed by Adam Rees, has been cross-checked many times with different standard candles and always lands on a higher value. On the other side are estimates drawn from the oldest light in the cosmos, the cosmic microwave background, most precisely mapped by the Planck satellite. From that pattern of faint radiation, cosmologists infer a current expansion rate of about 67.4. Between these two lies a 6 or 7 kilometer per second per megaparsec gap, seemingly small, but far beyond what error margins should permit. To grasp the intuition behind the dispute, it helps to outline the methods without dwelling on the technical minutiae. In the nearby universe, Type Ia supernovae serve as reliable standard candles. Their intrinsic brightness is well known, so if they appear dimmer than expected, the dimming reveals distance. Combined with redshift, this gives today's expansion rate directly. The other method reaches much further back in time, analyzing fluctuations frozen into the microwave background about 380,000 years after the Big Bang. From those early conditions, cosmologists use models of cosmic evolution to project forward and derive a predicted Hubble constant for today. Both techniques agree that the universe expands. They diverge on just how fast. When the James Webb Space Telescope entered the debate, expectations ran high. Its infrared capability allowed more precise measurement of Cepheid variable stars, essential rungs on the distance ladder, and the calibration of supernova distances to far greater clarity. Webb also gave a way to test alternate standard candles such as red giant branch stars, providing independent checks. By 2025, results from multiple teams had been published, and far from offering a single resolution, they broadened the discussion. On one hand, Rees and the SH0Es collaboration used Webb's improved Cepheid observations to reaffirm and strengthen the local expansion speed at about 73. The reduced observational scatter meant their error bars shrank, leaving the tension with Planck's 67.4 figure more firmly established rather than erased. On the other, Wendy Friedman and colleagues, working with Webb-calibrated tip of the red giant branch stars, reported a more moderate value of about 70.4 with roughly 3% uncertainty. Within those margins, their result overlaps with Planck's lower estimate. Instead of contradiction, this hinted at possible reconciliation, though not all astronomers are convinced. What Webb provided was not a decisive answer, but a clearer frame with which to test the discrepancy. This nuance matters. It is too simple to claim Webb deepened the conflict in a straightforward way. Rather, Webb refined both sides. Some datasets continue to favor the higher local measurements. Others lean toward intermediate numbers that reduce the gap, and the Planck figure remains consistent. The outcome is that the tension has become more sharply posed as an active, unresolved scientific question. It is no longer easy to dismiss one side as unreliable. Both approaches are now entrenched, cross-verified, and supported by Webb's precision. Why does this matter beyond numerical curiosity? The expansion rate sets the overall age of the cosmos, the timeline on which galaxies and stars form, and the inventory of cosmic ingredients. At about 67 kilometers per second per megaparsec, the universe would be around 13.8 billion years old. At about 73, the age would drop by several hundred million years. This difference directly connects to Webb's own early galaxy discoveries. A younger universe makes the presence of massive, mature galaxies at early times even harder to explain. Conversely, an older universe loosens the tension, but demands adjustments to how dark energy operates. The stakes extend deeper into physics. If we assume both high and low measurements are internally consistent, then additional elements of the universe may be missing from the standard model. Some theorists argue that dark energy might not be constant but could evolve in intensity over time, a scenario sometimes called early dark energy. Others propose the existence of new light particle species that behaved relativistically in the early universe and altered the physics behind the microwave background. Late-time modifications to gravity have also been entertained, with laws acting slightly differently across large cosmic scales. None of these proposals has yet secured decisive evidence, but each represents a possible path to reconcile the mismatch. What Webb's data have done is strip away comfortable explanations. Instrumental error was once a candidate answer, but with upgraded observations across independent groups, that claim carries little weight now. Dust corrections, calibration errors, overlooked biases, all have been scrutinized with Webb's precise imaging and found inadequate to account for the scale of the gap on their own. This is why cosmologists continue to treat the Hubble tension as a frontier problem, a signal pointing to either overlooked physics in familiar components or the need to expand the framework itself. Conferences in 2025 reflected this shifting mood. Rather than arguing whether the tension exists, researchers focused on what kind of physics could plausibly bridge it. Some favored incremental modifications that preserve the standard cosmological model's broad success, but add a subtle ingredient. Others were more willing to entertain bolder possibilities, from evolving dark energy fields to interactions with as yet unknown particles. But the emphasis in discussions remained grounded. Webb's measurements improved precision and clarified the debate. They did not settle it. For non-specialists, the dispute might seem too fine-grained to matter, but behind these differing numbers lies a blueprint of cosmic history. If the CMB reading at 67.4 is right, then today's universe emerged in lockstep with early predictions, and Webb's glimpses of rapid galactic growth must be explained another way. If the higher supernova measurement is right, then the universe is younger than thought, and nearly every aspect of structure formation is affected. If the intermediate Webb-based estimates hold, then the tension may soften but not disappear, hinting that something subtle shaped the early cosmos. By the end of 2025, consensus had not shifted toward resolution. The discussion now rests on how to interpret the measurements rather than whether they are trustworthy. Webb has acted as a referee, weighing in on both sides by refining observations of Cepheids, red giants, and galaxy clustering. Instead of dissolving the disagreement, the telescope has created sharper contours around the problem. The Hubble constant remains a live puzzle, one that threads through every model of cosmic history. And while debates continue over equations and calibration, the expansion rate question links back to the most concrete evidence Webb has already produced, the surprising maturity of galaxies in the early universe. Whatever the true value of the Hubble constant, it must be consistent with how structure emerged from the primordial darkness. This circles the conversation back to another frontier problem troubling cosmologists: matter itself, and the invisible form that accounts for most of it. Dark matter's unexpected role in early structures. Galaxies that arose within the universe's earliest few hundred million years were so massive that they exceeded every forecast of how quickly matter should collapse under gravity. If only ordinary matter had been responsible, there would not have been nearly enough time for such giant structures to assemble. The leading framework, therefore, turns to dark matter, the unseen component making up most of the mass of the cosmos. Webb's 2025 surveys of young clusters and faint galaxies provided some of the best maps yet of these ancient environments. Those maps showed early clustering signatures and gravitational lensing patterns that strongly suggest massive dark matter halos were already in place surprisingly early, or that the halos formed more efficiently than expected. In standard cosmological models, dark matter is treated as a patient background actor. Because it does not radiate, cool, or collide, it should clump together gradually, creating gravitational wells over long timescales. Only later would ordinary matter fall inside and ignite stars. Webb's observations complicate that picture. By a few 100 million years after the Big Bang, galaxies were already assembling within structured webs, their alignments consistent with underlying halos. The lensing of background light in these regions revealed hidden mass concentrations too large and too organized to fit slow growth predictions. Instead of diffuse wells deepening over eons, the data imply that dark matter halos had already collapsed into significant structures during cosmic dawn. The earliest clusters were especially telling. Galaxies were not scattered at random, but collected into knots and faint filaments, suggesting invisible gravitational skeletons already shaped the terrain. Lensing arcs revealed that unseen mass bent light across scales much denser than theory foresaw. To use one clear metaphor, these dark matter halos acted like submerged anchors, pulling ordinary matter quickly toward them. Gas and stars then gathered around those anchors far earlier than simulations predicted. Rather than lingering scaffolding slowly built in the background, dark matter appears to have defined the blueprint of the earliest galaxies from the outset. In some of Webb's best-studied regions, such as areas containing galaxies just 600 million years post-Big Bang, the signatures are consistent with furious star formation. These galaxies were burning gas rapidly, consuming material at paces unanticipated by existing equations. This intense activity fits neatly if dark matter wells were already deep, compressing and fouling gas with added force. Under those circumstances, collapse accelerates, and young stars appear at a remarkable tempo. What would normally stretch over billions of years instead played out within a fraction of the time. Such results expose a basic contradiction. Dark matter, treated as inert and non-collisional, should assemble lethargically at first. Cooling and radiation are unavailable to it, so collapse should drag on. Yet observations suggest the opposite, that halos capable of binding gas and organizing galaxies existed almost immediately. One possibility is that halos formed faster due to conditions in the early universe that models undershot. Another is that astrophysical processes around baryons, ordinary matter, were more efficient than imagined. For example, intense starbursts inside small galaxies, or direct collapse seeds funneling gas toward dense centers, could have accelerated growth alongside dark matter's gravity. By 2024-2025, both ideas were the subject of active research. Either dark matter organized sooner, or baryonic matter collapsed with more efficiency than expected. Each alone could help explain Webb's picture of galaxies maturing quickly. Support for a compressed timeline also appears in the chemistry of early galaxies. Heavy elements, oxygen, carbon, even traces of iron, showed up where they should not yet exist. Because such elements form in stars and are dispersed by supernovae, their early presence requires rapid and repeated stellar generations. The most plausible way for so much material to cycle through life and death so soon is if gas condensed into stars extremely quickly. And the easiest way to enforce that condensation is through dense halos that had already gathered. Without such invisible mass to pull material inward, timing would stretch, and the observed chemical enrichment would not occur. These insights reframe the division of work between visible and invisible matter. Instead of being a quiet framework into which galaxies later slipped, dark matter looks more like the prime architect setting the earliest structures. It determined where galaxies could emerge and how soon they did. If supported by continuing research, this perspective suggests our concept of dark matter is incomplete. Crucially, though, Webb has not demonstrated any exotic interactions beyond gravity. While some theories speculate faint self-interactions among dark matter particles, all such ideas remain conjectural. Earth-based detection programs, including underground detectors and collider experiments, have produced null results to date. Any new proposal must reconcile hints of rapid structure formation in the skies with a complete absence of particle signals in the lab. Webb also revealed not just isolated galaxies, but extended protoclusters. These were networks of systems linked into large-scale webs within the first billion years, far ahead of timelines in standard simulations. Modelers testing 2025 data found they had to allow dark matter halos to form and merge more quickly than usual to reproduce such webs. Without that adjustment, the density of galaxies and the richness of clustering could not be matched. This tension forces cosmologists into open debate. If halos clumped faster at early times, what properties gave them that advantage? Were initial conditions, such as density fluctuations left from inflation, sharper than assumed? Were gas processes in smaller galaxies efficient enough to make the visible assembly appear faster than the halos themselves grew? At present, both explanations remain on the table, and new JWST surveys continue gathering constraints. The evidence also touches directly on another puzzle: the surprisingly rapid growth of black holes. If early halos were already massive, their central regions provided fertile ground where dense gas could collapse toward compact seeds. That framework could feed black holes to large masses much sooner than conventional accretion models predict. This connection has grown clearer as astronomers compare Webb's census of luminous quasars with companion halo simulations. More efficient early halo formation would align with both galaxy clusters and black holes exceeding expectations. Still, one caution underscores all of this. Webb provides strong evidence of early structure linked to dark matter, but it does not resolve the mechanism. Possible solutions: fast halo formation, more efficient baryonic collapse, direct collapse black hole seeds, or combinations thereof, are hypotheses under active test. Observational astrophysics shows us the signatures. Theory must catch up without overstating what is proven. This care prevents overstretching into claims unsupported by the data. Ultimately, what makes Webb's dark matter results so significant is their cumulative weight. Different lines of evidence: galaxy clustering, gravitational lensing, chemical signatures, starburst rates, consistently indicate structure building at a pace classical models cannot match. That coherence has shifted the conversation. The issue is no longer whether something unusual is happening, but how it happened. Dark matter remains the prime candidate, but astrophysical additions such as direct collapse or early efficient star formation are now equal parts of the debate. For cosmologists, the implication is sweeping. If the unseen matter truly accelerated the assembly of galaxies, then many assumptions about cosmic chronology require updating. Ages assigned to stellar populations, rates of star formation, and levels of early element enrichment must all be recalibrated within a compressed timeline. Instead of galaxies slowly gathering over 2 or 3 billion years, entire systems arose within a few 100 million years, supported by backbone halos already waiting for them. Even with extensive data, the question remains alive. Does the acceleration signal something intrinsic to dark matter itself, or to the way baryonic matter interacts within its gravitational grip? This distinction matters because it divides the explanatory burden between fundamental particle physics and astrophysical processes we can model in principle. Only continuing Webb observations combined with laboratory searches can refine that boundary. As of the close of 2025, the conclusion is careful but unavoidable. The invisible component of the cosmos cannot be considered inert scaffolding alone. JWST observations strengthen the view that massive halos were present astonishingly early, or that their formation was more efficient than predicted. Combined with astrophysical processes like direct collapse and high-efficiency starbursts, the picture is of a universe assembling its visible structures at breakneck speed. And yet, as galaxies aligned around unseen anchors, they also revealed something still harder to explain: the presence of enormous gravitational centers already blazing in the early cosmos. These black holes, discovered by Webb in the same epoch, strain credulity even more than accelerated galactic growth. The question of how such giants formed so soon now looms as the next great puzzle. Supermassive black holes too soon. The James Webb Space Telescope added a fresh complication in 2025 when it revealed quasars powered by black holes with inferred masses between 1 million and 1 billion suns at redshifts, corresponding to just 300 to 700 million years after the Big Bang. Interpreted conservatively, that means some of the universe's earliest luminous objects were already driven by enormous central engines. For models in which black holes begin as small stellar remnants and grow steadily through mergers and gas accretion, billions of years should be required to reach such scale. Yet Webb's data show that this type of mass appeared far earlier than standard timelines predict. To understand why this is troubling, it helps to outline how conventional growth works. A typical starting point is the collapse of a massive star, leaving behind a seed black hole a few times the sun's mass. Over cosmic history, the seed can accumulate gas from its surroundings or merge with similar remnants, each step contributing incremental growth. Even at the fastest allowed feeding rate, the Eddington limit, this doubling process takes considerable time. Reaching the billion solar mass range through this steady pathway should require long stretches of cosmic history, not just a few 100 million years. The Webb detections therefore strain the mechanics of black hole origins as currently described. Astrophysicists have outlined alternate pathways that may shorten the timeline. One widely discussed model is the formation of direct collapse black holes, where instead of fragmenting into stars, a pristine cloud of hydrogen gas collapses directly into a black hole of perhaps 10⁴ to 10⁵ solar masses. From such a large seed, the climb to millions or billions of solar masses can be completed more quickly. Other ideas include episodes of rapid, super Eddington accretion, in which matter falls in faster than usually permitted, or the formation of primordial black holes in the earliest instance of the universe, bypassing stellar collapse entirely. Each concept provides a potential route, though none has yet been supported by decisive observational evidence. Webb's observations also highlight that these black holes were not isolated curiosities. Many resided at the centers of galaxies, where intense star formation was already underway. Spectra showed powerful outflows, jets, and energetic winds, which indicated that the black holes were active, consuming matter and radiating prodigious energy. This introduces another tension. Feedback from an accreting black hole heats surrounding gas and should make further accretion more difficult. Yet in these early systems, growth occurred rapidly in both the black holes and their host galaxies. Instead of hindering development, feedback processes may have been intertwined with, or even fueling, rapid assembly. One striking case emerged in 2025 when Webb observations pinpointed a quasar powered by a black hole around 1 billion solar masses less than 500 million years after the Big Bang. The structural complexity of its host galaxy and the energy output from its bright disk underline the scale of the challenge. The presence of mature giants in what should be a juvenile cosmic setting is not explained away by small errors in mass estimates. Even conservative calculations leave them anomalously large. Several theoretical teams have turned back to fundamental physics for possible answers. Some examine whether dark matter distributions could have accelerated infall, channeling gas with unusual efficiency toward galactic centers. Others simulate the effects of dense early halos concentrating matter quickly enough to overcome the limits of gradual growth. Although encouraging hints exist in simulations, none reproduces the full scale of Webb's detections across so many systems. This pattern of repeated evidence suggests that what is observed is not a rare outlier, but rather a common feature of the early cosmos. The more speculative suggestions extend into ideas well outside standard astrophysics. One of these is that black holes observed so early are not fresh creations, but relics that predate the hot Big Bang phase. Hypotheses range from objects formed during phase transitions in the primordial plasma to relics persisting through cycles of cosmic contraction and rebirth. Within Roger Penrose's Conformal Cyclic Cosmology, For example, enormous black holes could, in principle, leave imprints carried into a succeeding eon. Importantly, even proponents acknowledge this is radical, and the wider community treats it as speculative rather than established. It is highlighted in discussion because Webb's data lends circumstantial motivation, not because it offers proven resolution. If such objects were indeed survivors, they would redefine our understanding of cosmic continuity across epochs. But this claim remains contested and requires extraordinary evidence. Even within astrophysical boundaries, uncertainty still leaves space for exploration. Super Eddington flows could, in rare conditions, allow small black holes to gain mass far faster than canonical limits suggest. The early universe, crowded with collapsing halos and turbulent flows, may have allowed such episodes, though no direct observation confirms them. Similarly, the possibility of direct collapse seeds remains an active subject of study. Certain environments with low metallicity and strong radiation backgrounds may suppress star formation and allow gas to collapse wholesale into massive black holes. With large seeds in place, the trajectory to the billion solar mass range becomes less exaggerated, though still compressed. What gives the early supermassive black hole population added significance is its potential impact on galaxy evolution. Black holes influence far more than their immediate surroundings. Their gravity stabilizes central regions, their outflows regulate star formation, and their energy output may contribute to reionizing large volumes of intergalactic hydrogen. If active supermassive black holes existed during the universe's first 500 million years, they were not simply exotic anomalies. They may have shaped how galaxies matured so quickly after the Big Bang. The very paradox of their early presence could dovetail with the surprise of fast-forming galaxies, making both phenomena parts of the same puzzle. One caution underscores the entire debate. Mass estimates of early black holes draw from the motion of gas close to their event horizons, inferred through emission line widths and luminosities. These techniques are widely trusted but not immune from calibration uncertainties. Researchers consistently check whether underestimated systematics could shrink the apparent problem. So far, however, refinements have reduced error margins but preserved the overall conclusion. Black holes of a billion solar masses or more existed when cosmology expected only smaller seeds. By late 2025, discussions within the field had taken on a more sober tone. Optimistic efforts to save conventional growth models with minor tweaks gave way to acknowledgement that Webb had uncovered a stubborn inconsistency. For some, the most likely answers lie in combinations of astrophysical processes working faster or more efficiently under early conditions. In particular, halos concentrating gas, direct collapse seeds, and episodes of rapid accretion. Others remain open to the possibility of unknown physics or speculative cyclic carryover, but always with the qualification that such ideas remain outside consensus. The narrative built from these observations is not only about black holes, but about cosmic timing itself. The speed with which complexity appeared in the first few hundred million years forces astronomers to revisit how they model the interplay of dark matter, gas, and feedback. It changes the balance between processes once thought slow and cumulative versus processes that may have run at breakneck pace under extreme conditions. Even though questions remain unresolved, the practical importance is clear. The earliest quasars demonstrate that the foundations of galaxies and their central engines were linked from the very start. If massive black holes existed early, then their gravitational dominance and radiation could act as accelerators in assembling mature galaxies far faster than expected. That possibility makes them not merely anomalies, but potential keys to why cosmic structures took shape so quickly. Seen in this light, Webb's findings shift the debate from whether such black holes exist to what mechanisms, whether astrophysical or exotic, allowed them to appear so soon. They stand as one of the most concrete mysteries pushing cosmologists toward new models of both growth and origin. And while black holes challenge our understanding from within, the sky also offers another enduring anomaly, one imprinted on the universe itself, waiting quietly in the background radiation to be explained. The cold spot and multiverse collisions. When astronomers first mapped the faint glow left from the Big Bang, they were struck by how uniform it appeared. The cosmic microwave background, or CMB, showed temperature differences across the sky amounting to less than 1 part in 100,000. That smoothness matched the expectation that inflation had stretched the early universe into near uniformity. But amid that faint radiation sat a feature that did not fit so comfortably. The cold spot, an unusually large, cooler region within the microwave map, was noticeably deeper than simple statistical models allowed. If the CMB is the fossil imprint of the infant universe, then the cold spot stands out as a mark that seemed out of place. Scientists initially argued it could simply be the product of random fluctuations, but the anomaly persisted through data from multiple missions, WMAP, Planck, and into Webb's era. By 2025, it remained one of cosmology's most enduring puzzles. As Webb's infrared surveys became available, astronomers gained a new opportunity to probe the landscape behind the cold spot. The telescope could not measure the microwave background directly. That was the domain of Planck. But it could peer farther into the regions of galaxy formation that lay in the same direction. The central question was whether a vast cosmic void could explain the anomaly. If the cold spot traced a region with much less matter than average, then both the distribution of galaxies and the CMB temperature dip might connect naturally. In this picture, photons traveling through the emptiness would lose energy, creating the cold signature we observe. To test that, Webb's deep observations mapped faint galaxies aligned behind the spot, looking for evidence that the region was truly underdense. What Webb found complicated the picture rather than resolving it. Some counts suggested sparser populations of galaxies in portions of the cold spot's direction, which would be consistent with a void. But other areas revealed distributions less easy to summarize. Clustering patterns hinted at unusual alignments and did not match simple simulations of what a spherical underdense patch should produce. Instead of confirming a void once and for all, the results undermined its simplicity. The cold spot continued to look like an area where multiple influences shaped the data. This lack of closure meant the anomaly could not be dismissed. Random statistical chance might still account for it, but the odds seemed uncomfortably low compared to what models predict. If the feature were simply a random blip, one would expect it to fade in significance as data improved. Yet each new map, with better resolution and cleaner noise subtraction, left the cold spot in place. Its persistence did not prove anything exotic, but it kept interest alive. Among the speculative interpretations, one that has attracted attention is the idea of a past collision between bubble universes. In models of eternal inflation, our universe forms as one pocket or bubble within a larger inflating field. Other bubbles form as well, each potentially with different physical properties. If one of these neighboring bubbles bumped into ours during the inflationary phase, the collision might leave marks carried forward to the CMB. These could appear as circular or asymmetric temperature patterns, a scar from contact at the edge of cosmic history. The cold spot's size and depth make it a tempting candidate for such a mark. Webb's 2025 results do not confirm this scenario, but they keep it from disappearing into speculation alone. By showing that the region's galaxy counts are not neatly explained by a void, Webb added constraints that theorists must explain. The irregularities seen in faint galaxy distributions leave open the need for explanations beyond a single underdensity. They do not amount to confirmation of a collision, but they ensure the multiverse hypothesis remains one of the possibilities still under consideration. To move beyond speculation, cosmologists point to specific predictions that could strengthen the case. A genuine collision imprint would ideally appear as two independent features lining up in position and scale. First, the CMB should show a distinctive localized asymmetry, such as the temperature drop already labeled as the cold spot. Second, galaxy surveys in the same direction should reveal distortions in clustering traceable to altered gravitational fields. Only if both signatures were found in firm correlation could the hypothesis gain stronger ground. At present, data remain inconclusive. Planck provides the CMB map, and Webb offers glimpses of galaxy patterning, but alignment evidence is tentative. The conservative view is that astrophysical or statistical factors may yet provide a solution. Dust contamination, foreground effects from intervening structures such as complex filaments, or even chance alignment of smaller voids could mimic a single great cold spot. None has been ruled out conclusively, yet no single conservative account eliminates the anomaly without leaving gaps. That refusal to settle the matter is what keeps the discussion active. By late 2025, conferences reflected a balance. Few researchers claimed that the cold spot definitively proved new physics, but fewer still were willing to call it irrelevant. Papers explored combinations of void-like underdensities, statistical tails, and exotic options, with Webb data contributing important boundary conditions. The telescope's infrared surveys clarified what galaxies are actually present in that region, trimming away some possibilities while sharpening others. The cold spot also resonates with a wider context. Alongside fast-growing galaxies, the Hubble constant tension, and early supermassive black holes, it adds another thread suggesting our origins may include features standard cosmology struggles to explain. Standing alone, the cold spot might be ignored as a rare fluctuation, but considered as part of a set of anomalies, it feeds the sense that the early universe may preserve deeper imprints than we thought. Cautious advocates of the collision hypothesis stress how testing should proceed. Next-generation CMB experiments will examine polarization patterns, seeking circular asymmetries that might align with existing temperature dips. Independent surveys of galaxies and weak lensing could confirm or deny whether matter distributions behind the cold spot show distortions incompatible with a void. Each provides a concrete criterion for making the hypothesis testable, rather than left as open speculation. For the public imagination, the cold spot invites reflection on whether we might already have indirect evidence that our universe is part of a larger system. Supporters frame it not as proof, but as a candidate signal, an encouragement to look more carefully, and to design observations with enough precision to probe beyond the model's limits. Critics, equally importantly, remind that extraordinary claims require much more than anomalies. Both positions influence how funding and new surveys take shape. Webb's contribution is best seen as a step in that testing. By linking galaxy counts to the CMB anomaly, it broadened the scope of what we can measure. Earlier, the cold spot was known purely as a microwave background feature. Now it is also known as a direction in which galaxy structures appear unusual. That does not make the multiverse conclusion inevitable, but it takes the problem from abstract map reading to something testable through independent probes. The cold spot remains exactly what it has been for years, an unresolved anomaly. Its endurance under scrutiny makes it important, but its cause is unsettled. One scenario, collision with another universe, remains conceivable but speculative and far from consensus. The more cautious appraisals emphasize either coincidental statistics or complex yet conventional astrophysics. Webb has ensured we cannot dismiss the anomaly, but it has not crowned a winner among the explanations. That uncertainty may be the point. Rather than being treated as an oddity to minimize, the cold spot continues to shape debates on what evidence would count as support for ideas once considered philosophical. It stands at the edge of science's ability to discriminate between what belongs firmly within the standard model and what whispers of frameworks yet to come. As research continues, some theorists draw connections between the cold spot and wider proposals about cycles or prior cosmic epochs. For them, anomalies in the microwave background may not only hint at collisions between universes, but also at relics from earlier phases of existence. The persistence of a feature like the cold spot, therefore, functions as a bridge between the practical mapping of structures with Webb today and more ambitious frameworks suggesting that our universe may have inherited traces from a past beyond the Big Bang. Penrose's cyclical universe theory revisited. Roger Penrose's Conformal Cyclic Cosmology, better known as CCC, offers one of the most ambitious alternatives to the standard picture of a single Big Bang. Penrose, a Nobel Prize-winning physicist, argues that the cosmos does not have one unique beginning or an absolute end. Instead, in his view, the universe unfolds in repeating cycles, or Aeons, each beginning with a Big Bang and ending in a state of extreme dilution. Where most cosmologists describe our universe as starting 13.8 billion years ago in a singular event, he imagines an infinite relay in which the ashes of one universe become the seeds of the next. And yet, while Penrose has unmatched authority in mathematics and physics, his proposal remains controversial, with key claims debated and non-replicated in independent analyses. At the heart of CCC is a mechanism for continuity between cycles. In Penrose's interpretation, the far-future universe does not vanish into nothing. It contracts neither into a singularity nor into collapse. Instead, black holes dominate, galaxies drift apart, and eventually all massive particles lose their rest mass through processes tied to particle decay and Hawking evaporation. When no mass remains, scale loses its meaning. An infinitely stretched, empty cosmos, stripped of matter, becomes geometrically equivalent to the hot, dense beginning of a new Big Bang. To Penrose, that conformal mapping links one Aeon's end directly to the next Aeon's start. A striking feature of the theory is his prediction of what he calls Hawking points. The idea builds from Stephen Hawking's insight that black holes slowly emit radiation and eventually disappear. In CCC, when the largest black holes evaporate in the end stages of an Aeon, they release bursts of energy that persist in the conformal transition. These bursts, Penrose suggests, become visible in the next cycle as faint, circular patterns in the cosmic microwave background. He and collaborators claim that what we see today contains imprints, tiny hot spots with circular boundaries, that could be the fossil signatures of evaporating black holes from the Aeon before ours. The proposal is attractive because it makes a concrete, testable prediction. Nevertheless, here the controversy becomes essential to address. When Penrose and colleagues first announced evidence for these concentric circles in microwave background data, other teams quickly attempted replication. Subsequent reanalyses by independent groups concluded that the claimed signals were statistically insignificant when proper randomization tests were applied. In particular, several peer-reviewed studies argued that the supposed Hawking points arose naturally from noise, map smoothing, or selection bias. As a result, the consensus within cosmology is that the claimed detections did not survive scrutiny. Penrose maintains confidence in his interpretation, but the wider community regards the signals as unconfirmed and controversial. This is an important caveat for viewers. Penrose is highly credible and his mathematics has shaped physics for decades, but CCC is not accepted as mainstream. Its most dramatic claims remain debated, and confirmation requires stronger, replicable evidence than has yet been obtained. Presenting it as an active hypothesis rather than settled fact preserves trust in the scientific process. The controversy is not a weakness to ignore, but an example of how extraordinary claims demand extraordinary verification. Although Webb itself cannot see Hawking points, the telescope is blind to microwave radiation. Its discoveries of mature structures at unexpected times have encouraged physicists to revisit CCC as one framework that might encompass these anomalies. From Penrose's perspective, galaxies appearing too massive, too early, or black holes growing at impossible speeds are not paradoxes to be patched with ad hoc fixes. Instead, they may result from inherited conditions carried across eons. While this interpretation remains speculative, it illustrates how Webb's data encourage cosmologists to consider alternatives that had been set aside for years. In 2025, interest in cycles gained momentum because Webb's evidence multiplied across domains: galaxy clustering, enrichment levels, supermassive black holes. Some researchers began asking whether these anomalies taken together indicated that the universe did not emerge in pristine simplicity but carried memory from a prior epoch. To be clear, this is not proof of CCC. Most cosmologists still prioritize refining early galaxy formation models, investigating dark matter halo growth, and testing variations of inflation. Still, the cumulative weight of Webb's anomalies has moved CCC from complete fringe status to a hypothesis some researchers consider in the mix when discussing what might replace or supplement inflation. The conceptual appeal of CCC is clear. It provides not just explanations for individual early surprises, but a unifying narrative. The universe's rapid early structuring can be reframed as a continuation, not a fresh start. Black holes that seem impossibly large within hundreds of millions of years could, in this view, be carryovers. The persistent Hubble constant tension could point not just to data uncertainties, but to boundary conditions passed down from a prior Aeon. Rather than positing one final answer, CCC reframes the story. Anomalies are not random deviations but integral features of a universe with history deeper than the Big Bang itself. Yet researchers remain measured. The conventional cosmological model, though imperfect, has explained large-scale structures, expansion and background radiation with comparatively few assumptions. By contrast, CCC requires the bold step of envisioning universes without beginning or end, stitched together through abstract geometry. For many physicists, the evidential bar for accepting such a radical shift remains unmet. CCC is stimulating, but as of 2025, it still lives on the contested margins of cosmology. Some of Webb's clues add to the intrigue. Elemental abundances in very early galaxies appeared richer than expected if those stars had only just emerged. Star populations seem to have lived and died, enriching gas faster than anticipated. To Penrose's supporters, this resembles the effect of an inherited chemical head start, consistent with matter cycles across eons. To critics, it signals the need for improved stellar formation models or more accurate understanding of dust and metallicity effects. Again, the same observation can be interpreted through multiple lenses, and only further data will tell which is correct. The conceptual bridge Penrose builds also sidesteps the question of singularities. Conventional cosmology admits a boundary at the Big Bang, where our equations break. Quantum gravity remains unfinished, and singularities mark zones beyond current physics. CCC offers continuity instead, no absolute beginning, but a handoff from one geometric state to another. In principle, this avoids singularities while still aligning with known physics in the observable range. Critics argue that the mathematics, elegant though it is, remains more suggestive than demonstrative. Webb's detection of multiple supermassive black holes at astonishingly early epochs provides one of the strongest points of resonance. Black holes play the starring role in CCC, as their late-time evaporation drives the imprint of one Aeon into the next. Seeing them appear consistently at redshifts where they should not exist lends rhetorical weight to Penrose's emphasis on their importance. However, mainstream astrophysics explains them through routes like direct collapse or super-Eddington accretion, without invoking cyclical cosmology. Discriminating between these possibilities requires much finer tests than Webb alone can provide. Critics of CCC have raised a sharp practical question. Could information really pass from a universe stretched to infinite scale into a new compact state? If all distances lose meaning and all material objects decay away, what preserves any structure? Penrose's answer relies on conformal geometry, in which stretching by infinite scales can be mapped equivalently onto compression to zero size if no massive particles remain. In such a conformal picture, bursts of Hawking radiation survive as timeless, scale-free features, ready to seed the next era. Although mathematically consistent within his framework, this remains difficult for many physicists to accept without observational evidence. The broader scientific process has reflected this tension. Several groups in the past decade combed the Planck and WMAP-CMB maps for Penrose's concentric rings or Hawking points, sometimes publishing candidate detections, but often concluding they matched chance fluctuations. By 2025, there was no consensus replication. CCC did, however, remain part of the discussion at conferences precisely because Webb's findings left so many open questions. Even if Hawking points are not yet confirmed, the idea keeps cosmologists asking how to frame anomalies in the bigger picture. The cycle of critique itself illustrates science at work. Penrose proposed an audacious theory. Others tested its predictions and often found them insufficient. He continues to defend his analysis. Others remain skeptical. Meanwhile, data from Webb does not prove or disprove CCC, but provides new grounds on which it might be evaluated. In this way, CCC functions less as an established truth than as a provocative hypothesis that prepares the community to recognize if truly anomalous patterns eventually do appear. By the end of 2025, the position of CCC was ambivalent but stronger than a decade before. Not because it had been proved, the evidence for its key signatures remained unverified, but because Webb uncovered enough surprises to make cosmologists hesitate before dismissing any serious alternative framework. Penrose's proposal thus remains active but contested, a minority position drawing attention precisely because the universe appeared less simple than consensus predicted. In public discourse, the notion of an infinite sequence of universes resonates widely. The idea that time has no border and that traces of prior eons might still echo inside our cosmos appeals to imagination. Scientists stress caution, but they also recognize that engaging with bold models keeps cosmology from stagnating. Whether CCC will ultimately endure depends on whether future experiments, especially next-generation CMB polarization maps, can confirm or reject the existence of Hawking points with stronger confidence. Until then, CCC remains a case study in how theory and observation continuously recalibrate one another. The result is a more complex picture of cosmology than many expected even a few years ago. Standard models remain effective at explaining the broad outline, but Webb's results demanded that alternative visions at least be considered. Penrose's cycles, controversial yet mathematically rich, now occupy a place in that conversation. And as the scope of inquiry widens from galaxies to black holes to background anomalies, some researchers extend the speculation further, asking whether the larger picture might also invite questions not just about prior universes, but perhaps even about signs within them that challenge us in still more unexpected ways. Hints of civilizations before the Big Bang. Could the universe itself contain traces not just of prior cycles, but of civilizations that might have existed before our own? This is among the most extreme lines of speculation triggered by recent discussions, and while almost no working cosmologists treat it as more than fringe philosophy, it continues to resurface when anomalies in the data appear persistent. The James Webb Space Telescope, with its sensitive 2025 surveys, sharpened patterns and fluctuations that had once been easy to dismiss as noise. In doing so, it gave fringe ideas new visibility, not because Webb detected signals of intelligence, but because its unprecedented resolution leaves less room to hide anomalies that resist standard explanations. These discussions center on irregularities that some interpret as structured. In maps of both radiation and matter distribution, one occasionally sees what look like repeating arcs, aligned clusters, or geometric arrangements. Previously, such features were written off as quirks of statistics within noisy measurements. Webb now provides much cleaner data, and in some cases the alignments remain. This is where speculative arguments arise. If natural mechanisms fail to neatly reproduce these arrangements, could they be intentional? Mainstream astronomers answer with caution. Geometry can emerge naturally from underlying physics and gravitational evolution. But the persistence of clean patterns in high-quality data keeps the question alive as a cultural thought experiment, even if most professionals regard it as unsupported. Some fringe voices have gone further, suggesting that if universes repeat, as Penrose's cycles envision, then a prior intelligent species might try to leave information imprinted into background signals, knowing physical survival was impossible. The concept imagines a civilization at the end of one universe, encoding data into the primordial conditions of the next. The medium might be the large-scale distribution of galaxies or slight irregularities in radiation. Such hypotheses attract attention because they feel like logical extensions of cyclical cosmology, but they remain technically untestable. More importantly, nothing in Webb's observations provides positive evidence of intention. What Webb does offer is sharper anomalies that stimulate this type of imaginative extension. Skeptics counter that human cognition has a known tendency toward pareidolia, the inclination to perceive meaningful patterns in randomness. We see faces in clouds, constellations in stars, and order in what may simply be statistical accident. At cosmic scales, with billions of galaxies and countless data points, low-probability alignments are not only possible but inevitable. The bar for calling such features evidence of intelligence is astronomically high. A true signal would have to be unmistakably non-random in a mathematically exacting way, displaying repetition, coding structures, or properties no physical process could produce. Nothing Webb found meets that standard. An important case discussed in 2025 involved galaxy distributions behind the cold spot. As Webb mapped faint sources there, recurring spacing patterns were noticed, almost concentric in nature. To most cosmologists, the explanation points toward statistical outliers, subtle gravitational lensing, or even chance alignment of cosmic structures compounded by measurement bias. A speculative minority suggested intentional modulation. Yet such arguments occupy the fringes because the evidence is equally, if not better, explained by ordinary processes. Where exotic physics like inflationary interactions or dark energy fluctuations could already serve, there is no need to invoke intelligence. Spectroscopic anomalies provide another example. Webb uncovered unusual element signatures in some early galaxies, with certain chemical ratios not matching current models. Mainstream astrophysics interprets these as signs of novel stellar populations or rapid feedback cycles not yet understood. A fringe idea, however, proposes these ratios resemble deliberate choices, a cosmic form of signal encoding by civilizations aiming for persistence across cycles. But again, no evidence compels this conclusion. Proposing deliberate enrichment adds risk of category error, confusing natural astrophysical production with supposed design. Here, too, the mainstream interpretation relies on adjusting star formation models or supernova pathways, avoiding leaps to intentionality. The essential debate is not between equal possibilities, but between conventional physics with gaps and speculative ideas with no empirical support. Natural causes, be they complex galaxy formation processes, systematic biases, or exotic but testable physical processes, are overwhelmingly prioritized. The idea of past civilizations works as thought experiment or cultural metaphor, not as accepted cosmology. What Webb has done is remove the comfort of fuzzy data. Anomalies are now clearer, which ensures they cannot be ignored. But clearer anomalies do not mean encoded intelligence. They only mean our models must catch up to sharper observation. For communication value, scientists use this moment to emphasize a healthy skepticism. History shows how easily pattern seeing leads to error, from canals on Mars to claims of engineered megastructures around stars. Each time, better data or refined theory provided natural explanations. Today's situation likely follows the same path. Webb's high resolution has sharpened details that models struggle with at first, but which will probably be explained through astrophysical processes once understood more deeply. In other words, anomalies are engines of progress, not indicators of purposeful design. Still, the human attraction to these ideas is undeniable. Asking whether civilizations could survive beyond their universe stirs imagination. But inside scientific discourse, extraordinary claims require extraordinary evidence, and there is none here. To maintain rigor, cosmologists stress that aligning galaxies or irregular spectra cannot be treated as proof of design without overwhelming, replicable evidence. Fringe scenarios may entertain and inspire, but they remain speculation acknowledged as such. For audiences, one way to keep curiosity alive while guarding against overstatement is to frame questions around thresholds of evidence. What evidence would persuade you that something unnatural was at work? Ask yourself. If astronomers one day observed a perfectly repeating, universal code embedded across cosmic structures, a feature impossible for natural physics to mimic, would you call it intelligence or new physics we don't yet understand? Let us know in the comments what your threshold would be, and why. This puts the emphasis back on critical thinking rather than sensational proof. Mainstream responses to Webb's anomalies continue to concentrate on astrophysical explanations, unusual distributions driven by chaotic early galaxy formation, underestimated feedback cycles, or even interactions involving dark matter and dark energy. Some scientists argue that better statistical treatment, not cosmic messages, is what will clarify these patterns. Others note that as Webb expands its survey area, many features may resolve once larger samples diminish local irregularities. To date, that is the dominant expectation. The irregularities persist not because of intelligence, but because observational cosmology always begins with hints and only later refines them into laws. By the close of 2025, the situation stood balanced between fascination and caution. The fascination lies in Webb's ability to uncover anomalies with unprecedented clarity. The caution lies in how we interpret them. Intention remains unproven, and for most scientists, highly unlikely. Astrophysical explanations are both more parsimonious and more testable, but the persistence of anomalies ensures the subject cannot be fully dismissed in wider discussion. Even if speculative approaches never yield confirmation, they serve to remind how much in the cosmos remains unsolved. In some ways, the debate's true value lies in what it says about science itself. Fringe hypotheses gain attention when data challenge complacency, but ultimately science progresses by investigating natural explanations first. Webb has highlighted gaps in our understanding of early galaxy clustering, enrichment, and structure building. These are puzzles with real consequences for how cosmology advances. Speculative overlays remind us how imaginative interpretation can stretch too far, but without them, the excitement of questioning would diminish. Thus, hints of civilizations before the Big Bang remains just that, a question, not an answer. It has no evidential standing in mainstream science, but its persistence as an idea reflects both cultural curiosity and the gravity of cosmic mysteries revealed in new detail. Webb has amplified anomalies, and people project their hopes and narratives onto them. Yet professional cosmologists continue to stress that anomalous data demand patient, methodical study, not leaps to exotic conclusions. Even taken as speculation, the theme underscores how central anomalies have become to modern cosmology. Every persistent irregularity is a reminder that our theories are incomplete. And while some dream of encoded messages, the real story is that Webb's precision has made even subtle mismatches impossible to ignore. That sharpening of mystery, not the suggestion of alien civilizations, is what most excites researchers today. It points to physics still missing from our frameworks, and to a young universe that may not have played by the rules we see now. With this recognition, the question shifts again. Instead of asking if civilizations have marked the cosmos, scientists ask what physics governed when those markings, natural, not artificial, first emerged. That focus carries us from speculation about intentions to deeper inquiry about the rules that may have shaped cosmic dawn. As we turn to those rules, we meet another frontier, understanding how the earliest universe might have been governed not by classical physics at all, but by quantum principles whose signatures Webb has begun to illuminate. Quantum cosmology and strange early physics. At the deepest edge of what Webb has shown us lies a realm where the familiar laws of physics may not tell the full story, the regime of quantum cosmology and strange early physics. Classical cosmology depends on gravity to explain the motions of large bodies and on quantum mechanics to describe the behavior of particles. But when the universe was compressed into an unimaginably dense and energetic state, those frameworks could not be separated. This is where theorists turn to quantum cosmology, asking whether the earliest epochs obeyed rules that differ in key ways from those we experience today. Webb cannot directly peer into the Planck epoch, but its measurements of the first galaxies and quasars have provided indirect evidence that the cosmos at that stage may have been governed by unusual processes. One set of clues appeared in the light spectra of very young galaxies. By splitting their faint light into component wavelengths, Webb revealed the chemical fingerprints of gases and stars less than 1 billion years after the Big Bang. Instead of matching the gradual buildup predicted by canonical models, the spectra showed uneven distributions of elements. In particular, heavy elements like oxygen and carbon appeared in significant amounts far earlier than the standard timeline should allow. Hydrogen to helium ratios also deviated from expectations, suggesting that either star formation ran far faster than consensus models permit, or that other processes influenced nucleosynthesis in ways not yet accounted for. These enrichment levels highlight a tension in the classical picture. Textbook astrophysics assumes the first generation of stars formed only from hydrogen and helium, while heavier elements were produced later in stellar cores and dispersed through supernovae. That cycle is thought to require long stretches of time, billions of years across repeated stellar generations. But Webb's data show galaxies already rich in these elements only a few 100 million years after the Big Bang. One possibility is that star formation was extraordinarily efficient, with massive short-lived stars enriching their environments quickly. Another is that non-standard processes, such as unexpected pathways to nucleosynthesis, sped the cycle considerably. In either case, it strains expectations set by purely classical physics. Energy distributions within the light curves offer a further puzzle. In normal galaxies, starlight averages out into predictable spectra based on stellar populations and their temperatures. Webb's observations, however, often revealed irregular patterns, with certain wavelengths emphasized or suppressed in ways that do not match current stellar evolution models. Some astrophysicists interpret this as the result of extreme starburst episodes or unusual feedback processes. Others suggest that what we are seeing reflects underlying quantum fluctuations from the earliest field conditions of the universe, impressions of randomness imprinted on the cosmos itself. Distinguishing between astrophysical acceleration and physics beyond the standard model is now a central task. Emerging theories propose a range of possibilities. Some stay firmly within astrophysical territory, arguing that massive direct collapse stars or exotic stellar populations could race through life cycles and enrich galaxies almost immediately. Others consider mechanisms like inflattened self-interactions or early dark energy, which could have altered the expansion history and affected how structure assembled. Both are testable avenues, Direct collapse black holes and super-Eddington accretion may explain rapid black hole growth, while modifications to inflation might bring models closer to Webb's observations of clustering and mass distributions. Quantum cosmology represents a third path, an attempt to entertain the idea that the foundational rules during cosmic dawn diverged subtly from those of today. Webb's measurements from young quasars underscore how unsettled this period may have been. The emission lines produced by matter spiraling into early black holes look anomalous compared to later quasars of similar brightness. Ratios of certain ions appear skewed, and the continuum emission sometimes departs from expected curves. These mismatches could stem from astrophysical details, variations in gas composition, unusual feeding rates, or selection effects. But they also provide potential evidence that interactions between particles and radiation in the early universe operated differently. Rather than proving that physics itself changed, Webb highlights the era when that possibility must be kept in mind. A subset of theorists link these anomalies with cyclical cosmologies. In that context, unusual chemical ratios or clustering effects could be interpreted as inherited information from a prior cosmic epoch. From this perspective, the irregularities are not noise, but traces that bridge eons. Yet even advocates acknowledge that this interpretation demands extraordinary evidence, and current data do not rise to that level. The more cautious framing is that prior Eon inheritance remains among multiple competing ideas, on equal footing with other hypotheses that stay within tested physics. For now, it serves more as a motivating framework than as a confirmed explanation. Repeating inconsistencies across Webb's datasets lend weight to the argument that something fundamental is being missed. Dust grains made of heavy elements, usually thought to require long stellar lifetimes and repeated supernovae, are found abundantly in galaxies less than 1 billion years old. Clustering data suggest preferences in how galaxies collect, deviating from purely Gaussian distributions expected from simple inflationary models. One interpretation is that these features reflect natural variation in early star formation rates. Another is that they point toward quantum effects lingering at macroscopic scales, probabilities that favored faster pathways of assembly than later conditions allow. Time itself could have operated differently at those densities and energies, at least in the sense that probabilities rather than deterministic rules shaped the emergence of structures. What Webb observes as galaxies and quasars could in part be snapshots of improbable outcomes, frozen into reality through quantum processes. Under this interpretation, accelerated chemical enrichment, massive halos, and the anomalous brightness of early systems all become echoes of the probabilistic nature of the cosmos at its birth. That is not proof of a changed set of laws, but a reminder that classical approximations lose coherence when pushed back to the earliest stages. Some cosmologists remain firm that astrophysical solutions can eventually explain the anomalies without altering physics. Modified stellar initial mass functions, new treatments of feedback from supernovae, and higher efficiencies in early molecular cooling could, together, reduce the gap between models and observation. The possibility of direct collapse black holes serves as an astrophysical answer to rapidly grown quasars. Early dark energy meshes with inflationary models while allowing slightly different growth rates for structures. Each refinement could make Webb's results less startling without requiring new quantum frameworks. The weight of evidence must determine whether such conventional fixes suffice. Still, the attraction of quantum cosmology lies in its ability to connect many anomalies under a single umbrella. If the earliest universe was indeed dominated by quantum uncertainty, structure and chemistry could emerge more rapidly, and apparent shortcuts become natural rather than paradoxical. Paired with cyclic ideas, it even allows for discussions about continuity across epochs, though always framed as a speculative extension. More practically, it gives cosmologists a set of tools to devise new tests. from improved measurements of polarization in the CMB to detailed spectroscopy of more first-generation galaxies. In sum, Webb's discoveries have brought questions of quantum cosmology from abstract speculation into active scientific conversation. Heavy element abundances, irregular spectra, mismatched clustering, all these anomalies hint that something beyond standard astrophysical processes may be at work, but interpretations remain divided. Quantum cosmology offers one lens among several, not a settled answer. For now, the telescope has supplied clues, not confirmations. Future targeted observations will be necessary to determine whether quantum effects, exotic physics, or simply more efficient astrophysics shaped the universe's earliest age. This leaves today's cosmologists with a choice. Either refine existing models to account for the new evidence, or admit that the assumptions once thought secure may require a more fundamental revision. In that sense, Webb's results are less about solving mysteries outright and more about forcing a re-examination of the foundations themselves, opening the door to larger questions about how the universe's story can be coherently told. Reshaping the foundation of physics. When physics no longer matches observation, even the most durable structures of theory enter revision. This is the condition faced in 2025. With evidence mounting from Webb, the standard cosmological model no longer appears fully adequate. Its core has long explained the link between the Big Bang, the growth of galaxies, element production, and the influence of dark matter and dark energy. But Webb's findings, massive galaxies far too early, supermassive black holes assembled in record time, and expansion rates that conflict depending on method, are asking questions the model cannot comfortably answer. What looked like a settled story now feels like a framework under redesign. Consider the emergence of structure. Conventional models project that the cosmos took hundreds of millions of years to produce small, irregular systems, with larger galaxies growing slowly by mergers. Webb instead revealed candidates whose size and organization resemble the Milky Way less than 1 billion years after the Big Bang. In simulations, such objects appear only much later, unless assumptions about cooling rates, star formation efficiency, and halo collapse are altered in ways that stretch credibility. Here, timelines developed over decades confront direct challenge. Equally pressing are the quasars seen so early that their central engines must already measure millions or billions of solar masses. The step-by-step ladder of stellar collapse, gas accretion, and slow merging cannot assign them such rapid growth. Even extreme models struggle to compress the sequence to under 1 billion years, yet Webb clearly observes these luminous engines within the first few hundred million years. Current explanations require either new astrophysical processes like direct collapse or a shift in the physical framework itself. The Hubble constant has proven equally resistant. From local observations of Cepheid variables and supernovae, one finds an expansion rate near 73 km per second per megaparsec. From the microwave background, reconstructed through the geometry of the early universe, one derives 67.4. Webb's sharper data refined both sides without closing the gap. Independent analyses produce slightly differing results, but no side collapses. This stalemate suggests the issue goes beyond measurement. For many, it indicates that the dynamics of expansion require fresh theoretical extensions. Taken altogether, the anomalies are consistent across independent domains. Early galaxies, unexpectedly massive black holes, and a fractured expansion rate do not look like statistical flukes gathered by chance. Instead, they build into a pattern that cosmologists can no longer ignore. For years, adjustments allowed the standard model to absorb new evidence. By 2025, Webb had presented mismatches great enough that those adjustments now look more like patches than solutions. To respond, researchers are considering avenues long treated as peripheral. Some target the physics of the early universe, such as introducing light relic particles or testing early dark energy to explain altered expansion and structure growth. Others look to astrophysical solutions, with direct collapse black holes, rare bursts of super-Eddington accretion, or unusually efficient starbursts delivering accelerated growth within conventional rules. A third family explores modifications to gravity itself, suggesting that the law governing how mass bends space and time may shift subtly across cosmic scales. And some seek explanations in cyclical models and multiverse scenarios, where memory or influence from other eons reshaped what we see as the start. At this stage, no option dominates. Each brings testable proposals, and each opens lines of observation that Webb and other instruments can pursue. What unites them is recognition that the choice may not be between slightly better calibrations, but between distinct theoretical families. Mainstream fixes like refining dust corrections or recalibrating Cepheid distances are being exhausted. New physics or a shift in cosmological framework has entered the list of credible candidates. The situation can be summarized in 3 points. Webb has exposed anomalies consistent across galaxies, black holes, and cosmic expansion. Standard explanations rooted in measurement error or ordinary bias are largely exhausted. The path forward involves combining new targeted observations with tighter theoretical models that can be directly falsified against data. These 3 steps define the present moment in cosmology more clearly than any single anomaly could on its own. This does not mean every radical proposal is placed on equal ground. Physicists retain a strong preference for solutions that keep close to established results, adjusting parameters only where necessary. But the tone has shifted. Once, speculative models were most often discussed in peripheral sessions and thought experiments. Now they appear in mainstream debates and peer-reviewed work, considered openly as ways to address the accumulating tension. This is less about abandoning the Big Bang framework, and more about asking what new ingredients must be added around it. Webb's role has been decisive because it supplied anomalies that resist dismissal. The telescope does not trade in theory. It delivers spectra and images that stand as records of light traveling to us across immense stretches of time. When that light shows a galaxy more massive than expected at less than 1 billion years, or a quasar too luminous for its place on the timeline, the theory must adjust. The evidence cannot be chosen away. For many in the field, this represents a return to first principles. Physics is accountable to measurements first. A shift at this scale is not without precedent. The adoption of relativity at the start of the 20th century showed how established principles could be overturned by persistent mismatch between model and observation. The introduction of quantum mechanics followed a similar arc. What those moments share is that data forced re-examination and led to new paradigms. Webb's 2025 portfolio of results has initiated a process of similar scope, even if the outcome remains uncertain. Going forward, cosmologists expect the next decade of instruments to provide clarity. Deeper surveys will test whether early galaxies remain equally abundant when larger regions of sky are covered. More precise spectroscopy will check heavy element ratios to confirm or deny patterns that now suggest unusual nucleosynthesis. New CMB experiments will refine the expansion story, sharpening whether early dark energy or another mechanism must be introduced. Theoretical progress will likely accompany these datasets, as models compete to account for what Webb revealed. For students of science, this is a reminder that knowledge is provisional. Textbooks written only years ago described a coherent progression from early density fluctuations to structured galaxies. They outlined a near-complete picture. Today, new evidence has torn open seams that once looked secure. The field that seemed to be closing in on completeness is now expanding again with fresh questions at its boundary. That expansion of questions is not weakness but strength. It demonstrates the health of a science that adjusts itself to the universe, not the other way around. In conversations among researchers, the mood has swung from incremental fine-tuning to questioning of underlying assumptions. Some press for aggressive refinement of astrophysical modeling, confident that with more complex star formation pathways, the anomalies can be folded into place. Others argue that the magnitude and consistency of the contradictions suggest the need for something deeper, a reshaping of fundamental theory to accommodate realities never considered. Both groups agree on one point. Webb has eliminated the option of declaring the case solved. The next phase will require careful balance. Speculative paths like cyclic cosmology or multiverse collisions inspire imagination, but their evidential foundation must be strengthened before they can command consensus. Astrophysical exactness remains the necessary filter through which all ideas pass, but the possibility that some anomalies represent genuine traces of prior or parallel universes cannot be dismissed outright, because the data resist simpler fixes. This duality, skeptical discipline combined with open acknowledgement of possibilities, is how the foundation of physics is now being reshaped. What emerges from this moment is a field at a crossroads. The universe looks different than expected, and the framework meant to explain it is under strain. Some anomalies may resolve within conventional astrophysics, while others may require concepts far outside the current standard. The key is that the data drive this change, forcing cosmology to test every alternative down to its limits. The momentum of this shift already points toward questions that extend beyond physics alone. If certain patterns survive standard explanations, they may link directly to scenarios where our universe is not isolated but connected to histories or structures before it. That possibility, even as speculation, sets the ground for the next stage of inquiry, a stage where cosmologists ask whether the scars of our beginnings might also be the remnants of something older. The cycle continues. Webb's discoveries have raised a central question. Are the anomalies we see signs of hidden physics, or hints that the universe itself may be cyclical? Galaxies that seem too large, black holes that grow too fast, mismatched expansion rates, and irregular background patterns all point toward puzzles still unresolved. None of these ideas are proven. Webb supplied striking clues, but consensus requires further cross-checks. Do you think the evidence leans toward new physics, a cyclic universe, or simply gaps in our models? Share your perspective in the comments. Whatever the outcome, Roger Penrose's work reminds us that ideas once abstract can become testable as our instruments gain reach.